This video is an explanation of the theory of computing atomic spin moments, ASMs, with the DDEC method. Magnetism in materials arises due to unpaired electrons, nuclear spins, orbital moments, or electric currents. In the present video, the focus is going to be on the materials that have unpaired electrons. Atomic spin moments, ASMs, quantify the net electron spin on an atom. ASMs can be computed by integrating the spin magnetization densities of a set of atoms in three directions. In collinear magnetism, the spin densities are projected onto a single direction. The spin of each electron either points in the same direction as the magnetic field, aka spin up, or in the opposite direction, aka spin down. Hence, the formula for ASM equals spin up minus spin down electrons, with the result being a scalar. Any real number value of ASMs is possible. For example, the magnetism of certain atom can have 8.4 spin up and 9.3 spin down character, and the ASM is going to be negative 0.9. Examples of collinear magnetism include ferromagnetic, antiferromagnetic, ferrimagnetic, and others. The arrows in this picture symbolize the net magnetic spin moments on individual atoms in the material, that is, ASMs. In ferromagnetic materials, all the ASMs point in the same direction. In antiferromagnetic materials, ASMs of equal magnitudes alternate in opposite directions. In ferrimagnetic materials, ASMs alternate in opposite directions but have different magnitudes. Now I want to explain the relationship between the spin measured along the z-axis as z and the ASM. In collinear magnetism, the z-axis is normally taken to be the direction along which spins are aligned. ASMs count number of electrons. In collinear magnetism, the ASM equals the number of spin up minus spin down electrons assigned to an atom. Sz is the electron spin measured along the z-axis. Since each electron has a spin of 1/2, the relationship between Sz and ASM for each atom in the material is Sz assigned to an atom equals ASM times 1/2. For example, an isolated nitrogen atom has 5 spin-up electrons and 2 spin-down electrons, giving ASM of 5 minus 2 equals positive 3. The Sz value for the isolated nitrogen atom is positive 3 times 1/2 spin per electron equals 3/2. A similar relationship holds for non-collinear magnetism. Electron spin vector assigned to atom equals ASM of the vector times 1/2. In non-collinear magnetism, electron spins can point in any direction. Therefore, the spin densities must be integrated in three directions, resulting in a vector with a magnitude and direction for the atom. ASMs in systems with unpaired electrons have many purposes other than the previously presented. They are useful to understand existing materials and to design new materials by studying changes in magnetism as a function of chemical composition. They can also be used to develop interaction potentials for atomistic simulations to use for the study of larger systems. Mans and Scholl introduced a method for computing ASMs in 2011 as part of the DDEC method. This method partitions the total spin density among atoms in a material in order to reproduce the correct system spin density. To achieve high accuracy, this method optimizes the assigned atom in material spin densities to resemble proportional and spherically averaged distributions. It has a non-negative spin projected electron density to produce chemically meaningful ASMs. For both collinear and non-collinear magnetism, it uses an iterative scheme to rapidly converge to a unique minimum. It uses a cutoff radius to achieve linear scaling, computational time, and memory with increasing system size. The DDEC ASMs are approximately chemically consistent with assigned net atomic charges in order to get better representation of chemical features in materials. These materials were chosen to test the charge and spin consistency across different methods. In order to get better representation of various systems, they vary from light to heavy elements and 0 to 1 labile electron. In this table, we can observe that the DDEC, NAC, and ASM are the ones having the least mean absolute inconsistency between assigned NACs and ASMs, being 0.15 compared to 0.60 from the Hirschfeld HD method. Proof for the computational efficiency in noncollinear magnetism is presented here. The total time in the left y-axis required per atom on a single processor x-axis was approximately 12 seconds per atom to analyze the single molecule magnet. The method also had good parallelization efficiency across multiple computing cores. This figure shows the rate of ASM convergence is independent of the basis set and follows the same trend for collinear as for non-collinear magnetism. For all materials, computing ASMs is inexpensive and converges exponentially fast. For all materials, the ASM error on iteration j plus 1 is about 29% of that on iteration j. As shown here, this gives a linear relationship between the log of the ASM error, y-axis, and the iteration number, x-axis. ASMs have been calculated in the literature by using the ChargeMol program to perform DDEC analysis. Here are some of the examples. In this study, different surfaces of aluminum oxide were investigated to determine which one would better support rhodium metal clusters to form a catalyst. Rhodium clusters containing 1 to 5 atoms were studied. ASMs were calculated for the most stable configurations for each system in order to determine the spin distribution. Some of the clusters were found to have different ASMs for the gas phase cluster versus the supported cluster. The ASMs were also different for different size clusters. Rhodium summed ASMs for the analyzed clusters range from 0 to 5. A recent study analyzed the magnetic ordering of ground state transition metal dechalcogenides. Magnetic ground state was calculated using DFT and the Hayes-Kuseria-Enzernhof HSE functional. It was further elaborated by using the DDEC spin partitioning technique to explore the alignment of magnetic moments in each element in the materials shown. This showed that the magnetic ground state, previously thought to be ferromagnetic, consists of antiferrimagnetic ordering. These were the references used to make this video. We thank the NSF Award for making this video possible.